Hi everyone, my name is Freshtah Azimi. Today I'll walk you through question 1 of module 3. This assignment is about the simple multi-morbidity index, a method used in health research to measure how much each long-term condition adds to a patient's hospital stay. By the end of this presentation, you will understand how we use a grouped patient comparison approach to figure out the individual effect of each disease on how long a patient stays in the hospital. The core idea in this assignment is that if sicker patients stay longer in the hospital, then the length of their stay can be used as a measure of how serious their condition is. We identify patients who have a specific disease and patients who do not. But the important part is that we can make sure both groups have the exact same set of other conditions. This matching process removes any outside forces that could affect the result. So the difference in hospital stay length we see can be linked directly to the disease we are studying. We apply this approach to 6 conditions: CHF, MI, diabetes, hypertension, alcohol use disorder, and ACL surgery. For each of the 6 diseases, we build a comparison table where every row represents a unique combination for other conditions a patient may have. For example, patients who have both CHF and diabetes but none of the other conditions. Within each group, we calculate the average hospital stay length separately for patients who have the disease and patients who do not. The effect of a disease within each group is simply the difference between those two averages. We then bring all the groups together, giving more weight to the larger groups to come up with the one final score that tells us how serious that disease is. Here you can see the raw data set. Each row is a hospital encounter. The key columns are LOS as our numeric outcome and the binary indicators for each disease coded as 0 or 1. Notice some patients have multiple conditions. This is why we need a stratification rather than simple means. A patient with both MI and CHF will have a longer stay due to both conditions. Our outcome variable LOS is right skewed, as is typical for hospital stay data. Most patients leave quickly, but a subset has very long stays. The binary disease indicator were derived from ICD-9 diagnosis code. We answer this question in 4 phases. In phase 1, we load the data file. We make sure each column is the correct data type and confirm that all disease columns are coded as simple yes or no values, which is 1 or 0. In phase 2, we create a label for each disease that identifies which other diseases each patient has. This label is what we use to group patients with the same health profile together. In phase 3, we calculate the average hospital stay length separately for patients who have the disease, which is the cases, and patients who do not have the disease, which is the control group, within each patient group. In phase 4, we combine the two sets of results, cases and controls, by matching on the patient group label, then calculate the difference in average stay length to get the severity score for each disease. Now, let's walk through the code step by step. In step 1, we load the dataset using Pandas read CSV. We immediately perform a data quality check, verifying column names, checking for missing values, and confirming that all disease indicators are strictly binary. It's a good practice to print the shape and head of the data frame to confirm successful ingestion. Notice we also inspect the LOS distribution here. The mean is around 5 days, but the standard deviation is large, confirming the right skew we would expect. In step 2, we convert any diagnosis codes into simple yes-no values, 1 or 0. If your data uses medical coding systems, you would do that conversion here. In our case, the data was already in yes or no format, so this step just double checks that everything looks correct. We make sure each disease column contains only zeros and ones with no missing values. We also create a combined label for each patient that lists all their other conditions, which we will use to match patients together in a later step. This label format is required for the grouping and matching functions we used in this code. In step 3, we filter the data to only include patients who have the disease we are studying. We then group patients by their shared health profile label and calculate the average hospital stay length and the total number of patients in each group. This gives us a summary table where each row represents one patient group, showing the average stay and how many patients are in it. We save this as our cases table. The patient count in each group is important. It will be used later to make sure larger groups have more influence on the final severity score. Step 4 works the same way as step 3, but this time we filter the data to only include patients who do not have the disease we are studying. We group them by the same health profile label and calculate the average hospital stay for each group. One important detail, not every patient group in the cases table will have a matching group in the controls table, and the other way around. We keep only the groups that appear in both tables. This makes sure we are always making fair, like-for-like comparisons. Any patient group that only appears on one side is left out of the final severity calculations. After we calculate the average hospital stay for each patient group, we check the results before moving on. We make sure the group size look reasonable, that all stay lengths are positive numbers, and that no group has an unusually high or unusually low number of patients that might suggest a mistake in the data. This check helps us catch any errors early before they affect the final result. We then print out the largest patient group in order of size, which gives us a sense of how common different combinations of conditions are across our patients. Here we can combine the cases table and the controls table by matching on the shared health profile label. Then we calculate the difference in average hospital stay for each patient group. Um, A positive difference means patients who have the disease stay longer in the hospital than matched patients who do not, which confirms that the disease adds to how sick a patient is. A negative difference would be unusual and worth looking into. We also calculate a range of likely values around each difference to double check that our results are reliable. The severity score for each disease is the average difference in hospital stay across all the patients group, where larger groups count more toward the final results. In simple terms, we multiply each group's difference by its size, add all of those up, and then divide by the total number of patients. This approach makes sure that larger groups, which gives us more trustworthy results, have a bigger say in the final score. We carry this out using a built-in calculation method in Python that handles this efficiently, even when there are larger number of patient groups. So this is our final severity results. The numbers show how many extra days in the hospital each disease adds on average, after accounting for any other conditions the patients may have. Based on these results, CHF and MI tend to have the highest score, which matches what we would expect medically, since both of them are serious heart conditions that needs a lot of care. And also ACL surgery scores are very low, which shows that our index can tell the difference between a serious sudden illness and a planned procedure. In summary, we successfully built and tested a simple multi-morbidity index using a group patient comparison approach. Our result matched the expected values, and it is confirming that our method was carried out correctly. The three main things to take away are using hospital stay length to measure disease severity works well with standard hospital records data. Grouping patients by their health profile is essential to correctly separate out the effect of each individual disease, and averaging across groups in a size weighted way gives us an accurate final score. In the future, this work could be extended by adding more advanced statistical adjustments, reporting a range of likely values around each score, or applying the same method to bigger and more detailed databases. Thank you so much for taking your time. I'm happy to answer any questions that you might have. Bye.